Hello everyone, welcome to my programming club. Today we will be solving the problems of weekly contest 368. Okay, so let's begin with the problems of 368 contest. So the first problem is uh, minimum sum of mountain triplets, part 1. So you are given zero indexed array nums of integers. A triplet uh, is of indices I, j, and k such that I is smaller than j and j is smaller than k. So what the problem statement is saying here is, let's say array is given to you 1, 2, 3, 4, and then 3 to 1. So a valid triplet that can be considered here is let's mark the indices first. 0, 1, 2, 3, 4, 5, 6. Okay. So valid triplet can be in this form: I, j, and k with their indices 0, 2, and 3. It can be the elements will be 1, and on the second index it's 3, and on the third index it's 4. Okay, so it can be a triplet. So this triplet can be a mountain if following condition satisfies. Basically, element at, let's call this array as ARR, or let's call this array nums. Okay, nums seems to be a good name. Okay, nums. Then element at ith index should be lesser than the element at the jth index. Also, the element at jth index will be greater than the element at jth index. So this should be something like this: I, j, k. So their elements should be like will be nums of k. So equality will not be there. So it will represent a peak-like structure. Okay. So this is a triplet which can be considered as a mountain. Triplet that can be considered a mountain. Okay. So what the problem statement is asking you to do is return the minimum possible sum of the mountain triplet of this nums array. So we have to minimize their sums. What we have to minimize? Sum. Sum is what? Sum of these numbers in the triplet. Okay. Sums of j plus. This is what you have to minimize. So how we will be doing that? So let's have a look at the constraints. The constraints here are pretty low. Okay, so along with this problem, we will be solving this problem also. This is part 2 of this problem. All things are same. Other than that, the constraints here are pretty high as compared to the previous problem. So we will be try to implement a solution that will work in both of them. It will save us some time. If in contest such problems are there that the only the constraints are higher, I think it's a good idea to solve both of them in one go. So the size of the nums array is given to be of order 10 raised to power 5. So a n square solution will not work here. Why it will not work? It will be 10 raised to power 5 whole square, which will be 10 raised to power 10 operations. Okay. And there is a operation limit of 10 raised to power 8 operations. Your number of uh, operations in your program should be lesser than this limit. And if it approaches to this limit and becomes greater than this limit, then you will get a TLE. So here our n log n solution will work. For anything below this, we will try to implement it in a of n complexity, time complexity, which will take you only 10 raised to power order of 10 raised to power 5 operations, and it will be lesser than 10 raised to power 8 limit on operations. Okay, so your solution will be accepted. Those of you who do not know what this limit is, so I will be providing a link of article describing how the time complexity of accepted solution varies according to input size. Okay, so without further delay, let's see how we will be solving. So for each index, let me change the color. For each index, what you will do is, if you know, let's say we are considering this index I and dx. If on left hand side we know what is the minimum element on left hand side, minimum on left, and let's say we also know minimum on right. Okay, then if let's call this element at this particular index as number num. So if there is some if the following condition satisfies, minimum on left is lesser than number and number is greater than minimum on right. Okay, then it's a valid triplet that can be called a mountain. That we can call mountain. Okay. So yeah, that's pretty much the idea of the solution. So among all these triplets, you will find the triplet with the minimum sum. Among all these, and the one with minimum sum. Okay, so how we will be doing that? So the only problem here is we for each index we have to know minimum on left and minimum on right. For that, it can be easily done with the help of array, two arrays. One will be storing minimum on left, and one will be storing minimum on right. Basically, what you will do is you will traverse the given nums array. Uh, Left to right to populate this particular array, and you will traverse right to left to populate or say fill this array minimum on right side. Okay, so let's have a look at the implementation. There it will be more clear to you how we are using these two arrays to find minimum on left and minimum. So these two arrays we used to find minimum on right, minimum on left, and minimum on right. You can say minimum element on left till a particular index, or say before a particular index. Minimum on right, minimum element on right for a particular index. So these two will be used for that. To fill minimum on left, you will traverse the given nums array in left to right direction. Okay, so and you will keep updating the values. Okay, and to find the minimum on right, you will traverse the given nums array in right to left direction. Okay, and that is how you will be doing that. And one more thing that I would like to mention is then you will initialize your minimum sum with maximum value. This is the value that you will be returning from your function, from your method also. Okay, and then for each index in range 1 to size -1. Why? Because we have to get at least 3 elements. To get at least 3 elements. Okay, for each index in range, this particular range, what you will do is find minimum element on its right and left sides. and if they satisfy the conditions to be a mountain triplet, then consider the sum of triplet elements to update the value of, and at last we will be returning your minimum sum. Okay, so that's how we will be solving this problem. So the overall time complexity will be order of n, where n is the size of the nums array. Okay, and the space complexity will be also order of n. Okay, so let's try to submit it once. As you can see, it's getting accepted. So this is, I have done submission for the second part, I think. Yeah, it will also work in the first part also. Let's try to submit it for the first part. Basically, it's the same thing. I have just not typed comment here. So let's try to submit it. As you can see, it's getting accepted for this one also. So two problems are solved. So let's move towards the third problem. So the third problem of contest is minimum number of groups to create a valid assignment. So you are given a zero indexed integer array nums, which is of length n. We want to group indices for each index I in the range of 0 to n minus 1. So it's a zero based indexing, and each index is assigned to exactly one group. So there will not be a case that two groups are having the same index. Okay, and a group assignment is considered valid if following two condition holds. What are those two conditions? The first condition being that uh, all the elements in a particular group should be having same value. Okay, all the indices that are in a particular group and the element of those indices should be same. So it's the same thing. And then let's say there are two groups, G1 and G2. So their sizes can be can have a difference of at max 1. Okay, so two groups should not differ by more than one size. Okay, let's say, let me take another slide. Let's say G1 group is having 3 members, which are nothing but indices, and G2 group is having 5 members. Then such a group assignment is not valid. What will be valid if, let's say, G1 is having 3 members and G2 is having, let's say, 2 members? So their difference is 1. Or let's say both of them are having same members, let's say 10 each, then it's also a valid assignment. Both of them are valid. This one is also valid. So both of them are valid. Okay, so this is what a valid assignment is looks like. Then let's have a look at the constraints. So the order of so the length of the array will be of order 10 raised to power 5. Okay, and elements are from 1 to 10 raised to power 9. Okay, So what we will do is we will try to solve this problem with a greedy approach. What the problem statement is asking you is you have to return an integer denoting the minimum number of groups that are needed to be created. So you are being asked to minimize the number of groups. So it's very much logical to think that to minimize the number of groups, you will be wanting to store maximum elements in a group, maximum members per se possible in a group. Okay, so we are concerned. What is the major factor that we are concerned with? Group size. So the larger is group size, the smaller will be your number of groups. Number of okay. So let's say uh, we capture the frequencies of each of the elements present in the array. Let's say the array being this. Okay. First step will be to capture frequencies of each element in array. Okay. So 1 is occurring, 2 is occurring, and 3 is occurring. 1 is occurring 3 times, 2 is occurring 2 times, and 3 is occurring 1 time. Okay. So you have to minimize the number of groups such that the assignment of groups is a valid assignment. Okay. So I will be doing that. Starting from the maximum group size, step 2 will be starting from maximum group size. We will check whether it can be possible to form a group groups with this group size. Also, there is a little thing that you have to keep in mind is, so let's say I propose a group size. Let's call this proposed group size. Okay. So the actual group size can be one of these three values. So, which is it can be proposed group size. Okay. It can be proposed group size plus 1. Let's ignore the spelling for now. I hope you are able to understand what I'm trying to say. So proposed group size minus 1. All of these are differing from the proposed group size by at max 1. Okay. So the difference here is 1. So the difference here is 1, and here it's 0 with the proposed group size. Okay. I think till now it's clear to you. So for each of the elements, for each of the proposed group size, we will check whether it can be possible. It can be possible to form a group with the proposed group size. Okay, so if it's possible, then you will calculate number of groups. Okay, and return the answer. Why returning answer here only? Because we are approaching group sizes in a greedy way. We are starting from maximum group size. So you may ask what will be the time complexity here. So let's say all elements are same. So starting from group size of 1 to 10 raised to power 5 maximum number of elements. So basically the time complexity here will be order of n itself. Okay, so let's say all the elements are same, then in this mapping that we have done, there will be only one element. And if let's say all the elements are different, then there will be at max 10 raised to power 5 elements. Both of these cases, your program will be running for order of n time, where n here is the length of your nums array. Okay, so it will pass the test cases since 10 raised to power 5 operations is lesser than 10 raised to power 8 operations. Okay, so let's see the implementation. How will be implementing the solution? First of all, we will capture the frequencies of each element. The given nums array or say vector. Okay, and then what you will do is you will find the element with maximum frequency. Okay, then you will greedily try to fit maximum elements in a single group to minimize the number of groups. Okay, if let's say the current group size that we are proposing is a valid one, then we will count the number of groups, count the number of and return them. Okay, and if any of the proposed group size is not possible, then you will return -1. If any of the proposed size is not possible, then you will return -1. Okay, so the main logic of the problem lies between these braces and this function, this group size possible. So what you will try to do is, let's say you know the frequency of an element and you are having proposed group size. Then you will find out for one how many uh, full groups with proposed group size you can form. Let's say your proposed group size was 3, okay, and your frequency was 5. So how many full size groups can be formed? 5 divided by 3, which will be 2. So full size groups can be formed. How many elements are left over after these full size groups? This you will find out. How many elements are left over after full size groups? How many elements will be left over? It will be nothing but 5 modulo 3. 5 divided by 3, what will be the remainder? Uh, so pardon here, pardon me, only one full size group will be there, okay, and for modulo it will be 2. So it will be something like this: 3 elements in a full size group, and 2 elements they will be left out. It will not be a full size group. So we will try to adjust these left out elements in these full size groups. What we will do, try to adjust left out elements in full size groups. By giving one extra element to each group, one extra element to each full size group. One extra element to each full size group. And if after this assignment there are still left out elements, then in that case groups with post group size cannot be formed. And if that's not the case, then they can be formed, and you will count the number of groups. So you may ask why we have done such a thing, that we are, distributing one extra element to each group to satisfy the condition that consider two groups G1 and G2. Their sizes can be differing by at most one. Okay, to satisfy this condition, we are distributing one to each. Okay, so this is the logic of the problem. Now let's move back to the implementation. So to implement this possible group size, we will calculate the left out elements, which will be nothing but element frequency minus proposed group size, modulo proposed group size. And then full size groups will be element frequency divided by proposed group size. Okay. In case there are no left out elements, you will be continuing with your check. In case there are no left out elements, then continue with your check. And in case there are left out elements, so group size can be one higher than or lower than the proposed group size. The difference between group sizes can at max be 1. So left out frequency can be adjusted in full size groups, some or all of them. Okay. So if there is a case that the number of full groups that are required, full size groups that are required is lesser than the number of uh, required slots, then you will return false. Okay. And you may ask why we have used such a statement, because all the left out frequency elements, left out elements will be lower than the proposed group size. That's why they are left out. So if you consider the previous example, in that the group size was 5 and your proposed group size was 3, and your frequency was 5. So if you see, you can form a full size group. This will be a full size group and 2 elements are left out. So this can only form group sizes of at max. Group size will be at max. Let me change the color. Group size minus 1. Because if let's say the size of this group would have been exactly equal to the proposed group size, then we would have formed a full size group with this, like this one. So, okay, that's why we are to calculate the required number of slots. We are using this -1, and to satisfy this condition that group sizes can only be differing by at most one value. Okay, so that's pretty much it. And if it's possible to form groups with such a group size, then you will count your number of groups. This will be the minimum groups required. So the full size groups that you can form plus left out elements. Left out elements will be accommodated fully in the uh, minimum full size groups. So you need not have to worry about them. Here, if there are left out elements, which could not be accommodated in full size groups, then you will distribute one each to full size groups, and the number of groups will not increase because of will not increase because of left out element. Okay, so then your minimum group size will be rated. Okay, and in case your left out elements, so actually the number of group size will increase if there are left out elements. It will increase by only one. So if there are left out elements, these were your left out elements, you will form a separate group of size proposed group size minus. Okay, so in that case you will just increment your uh, minimum groups required, and at last you will return your minimum group required. And that's pretty much is for the solution part. And if you are still having any doubts, please feel free to ask them in the comment section. I will be more than happy to answer them. So for the fourth problem, I was not able to solve it in the given time constraints of the contest while I was trying to solve. So I will try to solve it and upload a separate video for that if possible. So thank you for watching. Thanks.